Okay, so today we're moving on into Unit G, into input modeling, and I mentioned last time that there are cases like bimodality and things like that that we have to figure out a way to deal with, and so we'll talk about that a bit today. And then also generally, how do we deal with these data sets once we get them as we move toward finding a model for them. I want to briefly do a few slides on Lab 7, now that we're sort of in the back of Lab 7 here. And so this was the first lab where you've been introduced to this inventory simulation. If you remember from back way when we were talking about Excel-based methods, I mentioned that simulation is often used to investigate these inventory management problems. And this is one particular type of those problems, this SS inventory simulation, where gave you a kind of a model for you to work with, and then you had to rebuild that model using more advanced or more modern elements from Arena. And if you executed that, then you got something that looked like this sort of up here. So this was also meant to show you that along with getting data after your models, where that you can get sort of in those crystal reports, which, by the way, there are some questions on how do you export crystal reports to a PDF and things like that. I mentioned that I already put some Canvas announcements up a while back and augmented to one of the pages about getting data out of Arena for how you can do that. But sometimes you need real-time data, so data actually during your simulation, just to see if things are kind of doing, and part of it is just for debugging, but also it helps your stakeholder visualize what's going on. And that's some basic visualization stuff was added in this lab. So I just wanted to make sure everybody felt comfortable with this lab. So somebody, let's do this. Let's jump to, I will maybe put, I'm going to make this an attendance question as well. So, so I put the attendance question link in the chat, and I will also jump ahead to an attendance exercise slide here. And so the question I have here for us to then, and then we'll share this aloud as well, is in that model, what are little s and big S? So that's the question. So if you can, just in a couple of words, say what little s and big S are. And after you've entered your response into the attendance question, then what I want you to do is take your response and put it into the chat, but don't hit enter. So this is what some colleagues like to say is the enter key is lava. So just let it sit there in queue in the chat. And then, so take whatever your attendance response is, put it into the chat, and then when I say go, then everybody hits enter, and then we'll see a scroll of these responses here, just to see a survey of what people's responses were to little s and big S and how they relate to inventory management. So again, put your answer in the attendance question, and then also put it into the chat, and don't hit enter until I tell you. So I'll give you a couple of seconds for that, and then go ahead and hit enter in the chat, and let's see, let's sort of survey everybody. So hit enter. Expecting to see a few more responses than that. So again, we're just pasting in what you did for your attendance response into the chat here. And so we can kind of see what everybody's kind of collective understanding is of these quantities, little s and big S. All right, so in the answers that I got here, I see things like things about, so there's some, so I'm kind of looking down through, so all of these and seeing what kind of the quorum here. And it looks to me like the most common response is that little s is the minimum inventory needed before you trigger a reorder, and big S is the number that you reorder up to. And so, and that's right, that's what we're going to look for in these little s, big S inventory simulation models. The reason you get these fluctuations in inventory is that the inventory goes down and it hits some little s level, which then the inventory management person sees that and then orders up to big S, and then this can go on and on and on. And so you get these oscillations where you're ordering hopefully slightly more than you need at the instant, so that when people then make orders, then you deplete your inventory, but you never go into the point where you go negative. But so in this particular case, you see there's a bunch of cases where the inventory did go negative. And so perhaps big S needed to be increased, so they order more at the time, or maybe little less needed to be changed, so they order more frequently. So this is this is the idea that you're going to check your inventory once a day, and that could also be a random variable that you could adjust. And then you decide when to order more and how much to order, and that's what you're trying to optimize in this inventory management simulation. The reason I'm making sure that everybody has an understanding of this is that we will see this simulation model again. And so, so this inventory management model we will work with later in the semester as you'll kind of add some other things to it. So I want to make sure that people are kind of familiar with this model. All right, so so then without worrying about an attendance exercise, so if we look back at this model, we can see there are two types of entities. Maybe it's easier to look in this one where it's not running. And so what are the types of entities in this model? So we normally talk about customers as one type of entity. What's the second type of entity that was used in this model? Anybody? All right, I see a couple of answers in the chat. And those are different people than answered before, so I like that. I'm glad to see that. So yeah, so the answers in the chat is that the second entity type is the inventory evaluator. And so in this old way of writing arena models, you actually had to have the entities there on the model. So in the new arena, they're in that kind of spreadsheet view in that data module that's on the side. But in this older way of writing these arena models, you actually dragged in an entities block, and that's where you defined all your entities. And then they got listed down here when your model was not running. And so you can see that customer is one entity and inventory evaluator is another entity. So this is an example of how you're using an entity to actually do something which is basically programmatic. So up here, across the top here, you've got this little parallel block where you're creating an, in the middle here, you're creating an inventory evaluator. And then that inventory evaluator is analyzing the inventory level and deciding whether to do an order. And then while the order is out, the inventory evaluator just sits into a lag, a delay. And then once the delay is finished, when the new inventory has arrived, it gets added to the current inventory. That's what's going on here in the assign. And then that inventory evaluator moves away. And that inventory evaluator, that evaluation interval has been set up deterministically. It could have been set randomly, but it's just set, say, every day to do that. So that's an example where if you were writing this in sort of a more conventional programming language, you might imagine just having some sort of for loop or something like that, where it iterates through and every day it goes and checks this. So, but the way this was implemented here is they actually created an entity. Now in a real system, that entity may be a real person. You might have actually hired somebody to walk down through the warehouse and count up all of your inventory. Or it might be electronic inventory, and you're just saying, when do we decide when to do the next orders? And then that is just it's in an electronic schedule somewhere where it checks the electronic inventory every day. So even in that virtual case, we can still simulate it as if it's a real entity moving through the system. And so that's something I really wanted to highlight here, is that it was convenient in the inventory management model to create a kind of virtual entity, this inventory evaluator, as if there was a person that was actually checking the inventory every day, even if it's not implemented that way. For those of you who might implement traffic simulations for your final project, a very common approach is to do something similar for when the lights are changed. You can simulate a traffic light evaluator that comes by every traffic cycle and then decides to switch the traffic lights, as if there was a traffic cop standing at the corner who just stood there and arrived at, it's almost like a traffic cop's arriving regularly. So every 5 minutes, you get a new traffic cop who comes to the corner, unlocks the box, changes the signal, leaves, and then a new traffic cop comes by and does that same thing over and over again. And that is just an easy way to get these periodic events to show up in your simulation model, is to simulate them as if they're entities arriving to the system. So I wanted to see if there are any questions about that. Is that clear how the inventory evaluator was treated like a parallel type of entity, even though you might not think of them as a physical entity in the real world? So it's a really important tool to be able to use when you're writing these models. All right, so other things I wanted to highlight is the state variable here. So, we've learned what a state variable is, but we haven't had a lot of models so far in ARENA where we had to manage a state variable until this model. So what was the state variable that was used in this model? So I can go back to this model here. And so, yeah, what was, now you can see like under variables here, there's a lot going on here, but I would say that a lot of these variables are parameters, and some of these variables are these cumulative statistics. So what was the state variable in this inventory management model? Any guesses on that? And the thing about a state variable is something which is changing from event to event. And I'm seeing a couple answers come in. Appreciate those. So any other answers, any other guesses as to what the state variable is in this? Again, what is the thing that is changing? Whenever a customer arrives, it changes. Whenever an inventory evaluator arrives, it potentially changes. And the inventory evaluator, its behavior may depend on the state variable. So that's the key difference between a cumulative statistic and a state variable, is that the cumulative statistics do not change the behavior of the entities or the processes. They just take data for you to use as the designer afterwards. But the state variable can actually be referenced by the entities in the sim, and then they can alter their logic. And so the state variable here is the inventory level. So it's the first variable under the variables list in this model here. And so that's something that has to be initialized. You have to come up with an initial inventory level. So that's what's being plotted here. In this case, it was initialized at like 60. And so you see that it falls until it hits some low level. And then there was probably a reorder, but that reorder took delay. So it kept falling below 0 until finally you got an arrival of new product, and then you get this oscillation. So the state variable here is the inventory level. The inventory evaluator responds to it, and whenever customers arrive and make orders, they change it. So that is a variable that's behind the scenes. It's not an attribute because it's not attributed to any individual entity. It is a background sort of attribute of the system. It just sits there as a variable, a global variable that all can view and all can access to and change. Okay. So, and then we could talk about the 4 types of costs here. So I'm not going to go into this much in detail, but this is getting into like inventory management. And so those of you who do operations research work in the future, if you're doing inventory management models, then you'll find that there are 4, there are multiple costs that are associated with inventory management. And there's of course the ordering cost, like how much does it cost to actually to actually make orders. But then there are, that ordering cost, you've got the setup cost of just the general background cost of an order, and then the incremental cost where depending on how many you order, you're going to have each one of them cost more. So if you order a lot, then the order goes up. And so you have those 2 things that have to kind of add together. You have this unit holding cost and this unit storage costs. And so, these 2, again, are costs that have to do with how much inventory is on hand. So you have to pay for that space. If your warehouse is filled up with toilet paper, then you can't stock, batteries. So there is a cost, you have to pay the rent for the warehouse. And then you have a finite number of space in that warehouse. And so you can actually kind of charge rent to everything that's stored in that warehouse. So that's a holding cost. But then also when you go to a shortage, there can be a shortage cost. And so this shortage cost could be dollars lost to orders that were made elsewhere, that you lost that order. Or you could just penalize, you could discount the rewards that you would have got today that you have to get later because your customer is not willing to pay you until the stuff is shipped. And so you can use an interest rate calculation, present value of money. So go back to engineering economics, your F over P's and your P over F's, and you can do, a P over F calculation of, well, how much is that future order, that future dollar is going to be worth today. And if it's the same cost later as it is today, then I actually lost money on it. And that lost money could be what I put into my shortage cost. So when you're managing inventories, you have all of these costs you have to deal with because you can't just order every day because the setup cost of each order, maybe, it's not free to make these orders. Maybe it's not free to do the inventory check. So you can't order super frequently, but you also can't order a whole lot. Because if you order a whole lot, you're going to run out of space and maybe some of it's going to go stale. So in the news vendor problem, you add the additional issue that when you order inventory, eventually that inventory becomes unusable, just like a newspaper or a head of lettuce. So there's all of these things that you have to deal with that you can easily play with in simulation, but are maybe a little bit harder to deal with if you're just going to mathematically model them. All right. And then the last kind of thing that I want to make sure that people are comfortable with here is something that we already dealt with before the midterm, but in your inventory management model, you had to simulate a demand distribution. So every time a customer arrives, they either order 1, 2, 3, or 4 with different probabilities. And we implement that in Arena using this disk function. And so we have to make sure we're comfortable with running, with putting the parameters into this disk function. And so in this disk function here, you have to notice that even though the raw probabilities are given here, the cumulative probabilities end up being accumulating in the first, third, fifth, and seventh arguments here. So you have to turn the PDF or PMF into a CDF. And then if you replace this with a CDF, then you can load that up in the disk function. So that's how we get the disk function there. And then the even ones are just the outcomes here. So they typically are sorted, but they don't have to be. But when we talk about an empirical CDF, they do have to be sorted. So that's like on the midterm, talk about empirical CDFs. All right, so while I was talking there, I saw some microphones go off. Were there some questions? Okay. All right, and so, I mentioned that there are different ways to handle these inventory management problems that you might see in like a class like 470, but simulation ends up being a nice way to look at these problems, both to validate the theory that you learn in a class like 470, but also to work with more sophisticated problems and more realistic problems that maybe the frameworks you learned in 470 are not quite equipped to totally handle. All right, so that was our kind of post-lab 7. So any questions about the lab? Was the lab experience clear, this inventory management? Hopefully it was productive having to re-implement that old school model in the new school blocks. I'm hoping some of you learned a lot about Arena by forcing yourself to do that. Okay, great. All right, so let's move on to the main lecture then. So this week we have this Lab 8, which is an input, this goes along with our input modeling. So in Lab 8, I'm gonna give you a bunch of different data sets, and they're relatively realistic data sets, and you will have to use tools in Arena and tools that we're gonna talk about in lecture to try to find the right models for those data sets. And then those models, then you could then, in theory, use in a simulation later. So this is really meant to be preparation for your final project, where if you have data for your final project, you're going to need to then have a surrogate for that data that you implement in your simulation. So you'll need some input model that is an accurate representation of the real world data that you've gathered. And so that's what we practice in Lab 8. Then the next lab, there's no formal lab the next lab. So when we were meeting in person, we would be sort of be an open lab for people to come and work together. So you can kind of use that time as you wish to work with your team to sort of figure out where you're going to collect this data or how you're going to handle the input modeling problem, or at least finding these inputs. I've mentioned that this semester I can be a little more flexible if the system that you've chosen is not one that you feel comfortable taking data from due to COVID related situations. So it might be that you're going to handle a lot of data in lab 8, but then maybe in your actual input model for your system, you don't capture that data yourself. Maybe you have to go onto Google and do some background research and do some back of the envelope calculations. And then there was a question that was sent to me in the private chat here about histograms. If I ever ask you to generate a histogram, so in the lab 8, I'm going to ask you to generate histograms. And the question was, do the histograms need to come out of the input analyzer, a tool that will be introduced in lab 8, and then we'll also talk about a little bit in the lecture. The histograms that come out of the input analyzer are really ugly, and if you do decide to use them raw out of the input analyzer, you're going to need to annotate them with proper axes and things like that. So I'm really intending for most of you, although you can use the histograms in the input analyzer to give you an idea of whether the input analyzer has picked a good distribution, when you actually do a histogram for a report, you should do it in a cleaner tool like Microsoft Excel. So by now, due to previous homework, you now know how to do histograms in Excel. So bringing that data into an Excel and doing a properly formatted histogram is really preferable. The histogram you get in the input analyzer is really just meant to be a quick diagnostic for people. So I would prefer, and so then there's a further question in the private chat, should we use Excel or some other software then? I would prefer however you can prepare a histogram that looks clean for the grader and just generally professional. And in my opinion, the input analyzer histogram by itself isn't professional. If you really must use it, then you're going to need to sort of cleanly annotate it and clean up the histogram by drawing on top of it and something like that. So it's probably just easier using Excel. All right, or some other tool. If you want to use SPSS or SAS or whatever, Minitab, all of those are fine. MATLAB, that would be fine too. So I don't necessarily need to see the code for that, but I do need to see the data represented as a histogram, and I need to see where are your bins? How wide are your bins? So what are you binning? What is the y-axis? Is it frequency? So everything needs to be labeled and easy to read and clear what it is. So then, next week there will be no sort of formal lab, although all the labs are already available. So if you want to move on and keep doing the labs, that's fine. And then we have only 2 more labs after that, labs 9 and 10. They're on the regular schedule after that. Lab 10 actually introduces batching, and batching is related to this inventory management. So if you remember the muffin sim is kind of a combination of the inventory management from lab 7 and the batching you'll learn about in lab 10. And then we've got 2 open lab periods after that that are meant to provide you time to work on the final project. That's kind of the timeline moving forward. The final project, as we mentioned last time, it is posted. I talked about this all last time, so this is just here to be a reminder for those reviewing the slides. The most critical deliverables to worry about is that your, and I thought I put it here already in here, but or maybe I mentioned it up here, that I swear that when I was reviewing my slides last night, I saw that somewhere here I mentioned that, by the way, don't forget, on Friday, your team names are due. And so you're supposed to form your teams, and then you don't have to tell me what your system you're working on just yet, but you at least need to tell me who's in your teams. And every individual needs to submit that assignment so that I can see that every individual agrees on whose team that they're in. And then from those, I will then, so that'll be an easy grade as long as every individual has a submission that lists all the same members as every other individual that is in that team, then you'll get the credit for that. And then I will then form Canvas groups so that all future deliverables are group assignments where only one person has to submit. But for this assignment, every individual has to submit the names and their team names. So then a couple of other assignments here. We've got ICA G3, which will be due before lecture G3. That's next lecture. There is a homework that is out and available. It is technically not formally assigned until the next lecture. You don't like have everything you need for it yet, but if you'd like to get started on that, it's been available and it's out there. And then there's only one other homework after that. And that homework actually makes use of the inventory management that we did in Lab 7. So that homework is now available. The reason it wasn't available until now is that I wanted to make sure that like I am going to give you a model in J2 that you can feel free to use, and I wanted to make sure that that wasn't already given to you. So that's why I kind of put a guard on J2. But it should, I think, already be available in case you happen to get work far enough ahead. And in J2, you're going to make further modifications to the inventory management. You started in Lab 7. So again, yeah, here's where I was saying form your teams. The names of your team members are due Friday. And then as you form your teams, just start coming up with things that you could think of modeling with a discrete event system simulation. All right, so that was a mouthful. Are there any questions about the lab, about the timeline moving forward, anything like this? Okay. I'm not going to take the time to show you the midterm retake results. I can tell you they are very, very similar to the midterm results. There was the low score was a little bit higher. The average was maybe a percentage point or two higher. High score was the same. So, but of those people who took there were several students who increased their scores. But not every student took the midterm retake. So the overall average of the midterm has gone up after the retake, even though the statistics of the retake are very similar to the original midterm. So as you're thinking about moments in your head, you can figure out how all that stuff works. But so overall, looked like retake was very similar to midterm. All right, so if there are no other questions, then let's hop into this. So last time we were talking about input modeling and how to gather data for these problems. And so the input modeling was motivated by these simple systems like this one, where if you look at this create, process, and dispose, this structure is the structure of so many different, single server, single channel queuing systems. But the way we put different models into the arrival times and the service times totally changes the behavior of these systems. And that was something that if you go back to Lab 6, that's effectively what I asked you to do. In Lab 6, I had you build one of these, and then I had you change the random distributions in both the create block and in the process block, and then see how things changed. And I hope you saw that the performance metrics were very different depending on what you put in here. So the block diagram is not everything. It looks like it's everything, but what's inside the block diagram, the particular probability distributions you use, even if they have the same averages, if they are a different distribution, you get very different performance out. And so that's what we're talking about here, is how do we pick those properly. And so for queuing models, interarrival times and service times. For supply chain models, demand, we saw demand distributions in Lab 7, and lead time, we also saw that delay distribution in Lab 7. And then for reliability problems, failure times, all of these things could have very different distributions. So you have the exact same block diagram model. You can copy and paste from one company to another. But when you move to that other company, that same diagram is not going to work, because you might have a totally different distribution of, say, demand, for example. And so that's, we're trying to figure out what these distributions are and how do we build confidence that we've chosen the right distribution. So up until this point, we have talked about, well, if I gave you a distribution, how do you draw samples from it? That was all pre-midterm. And so that was, hypothesis testing. So this is the hypothetical distribution. How do you draw data that is, plausibly could have come from this hypothetical distribution? So, but now we're flipping that and we're saying, given data, how do I form that hypothetical distribution? How do I come up with a guess as to what distribution these came from, and then validate that guess? So we talked about collecting data last time, and now we're moving on to how do we identify that probability distribution. That'll be kind of our focus today. So if we go back to thinking about the metal detector example, then I want to take what we talked about last time and elaborate a little bit more on seeing that how do we deal with distributions that we see that do not look like any of the distributions we've learned about. So if you remember in the metal detector example, there were these people that go through a metal detector. And so the metal detector is the resource that they're waiting on, and there's only one of them. So it's got a fixed capacity of 1. Now, when they go through that metal detector, that's an activity. And so it's the time that they take to pass through that metal detector. And so inside Arena, you can, and I'll show you an example of this block diagram in the next slide, but you can create a create module to create all of the people. And then we are going to have a certain inter-arrival time in between them. Let's just say it's exponential. We're going to guess that for now. And then we can draw a process that has a seize, delay, release. So that process seizes a metal detector resource, so no other entity can use it, delays the entity for however long it takes to get through the metal detector, and then releases the metal detector, letting the entity move on and letting a new entity move into the metal detector. So that's what we mean by a seize, delay, release inside Arena, inside that process block. And so it's the delay that we are seeking the right model for. And then we've got that dispose. So that's what that looks like. So it looks just like that drilling center example. We've got our arrivals, got the single server, that's a single queue. There it is. So if I look at the real data, then I end up seeing that there is an average time through the metal detector of 30 seconds. Now, if you remember, 30 seconds seems like a long time to simply walk through a metal detector. A metal detector is pretty short. You might pause for a second before you walk through, but maybe it takes you 5 seconds, maybe 10 seconds to walk through a metal detector. So if we just took the 30 seconds and didn't think it through with our mental models, we might go back to our block diagram in Arena, and inside this go through metal detector in the middle, we might put an exponential with a mean of 30 seconds like this. Now, what that's going to do is in our simulated system, some of our entities are going to be way out here at like taking 3 minutes to move through the metal detector. There's no way a human is going to take 3 minutes to walk through a metal detector. So clearly this does not seem like this is capturing reality. So then the question is, what does the distribution look like in reality? And if we actually bin the distribution from reality into a histogram like this one, then it might reveal that we have 2 humps. We have an early hump that kind of looks sort of exponential and a late hump that's sort of symmetric. And so now we're sort of saying, how the heck am I going to generate a probabilistic model that looks like this bimodal distribution? I have not shown you in the class any hypothetical models that are bimodal, let alone this type of bimodal. So it's not like you can just go into and say, all right, this is an exponential 2 distribution or something like that. Like there is no distribution in Arena that is already pre-built for you that looks like this. One option you have is to use an empirical CDF. And so what you can do is take these data and sort them. And then you can plot the data sorted on this axis, and you can plot the rank. So this is just their rank divided by the total number of data on this axis. And you now have an empirical CDF where this hump here corresponds to this rise. This lull in between them is this constant part of the CDF. And then this hump is this rise over here. And so if I have that empirical CDF, I can then load that into a disk function. I'm just typing disk into the chat just to remind you that I could potentially load that into a disk and then load that into my Arena model. And then I've got my single server queue could possibly generate these bimodal times. But the worry is that if I just do that, if I just use a discrete distribution taken directly from the data, I'm going to miss an important feature of the physical system. So instead of doing that, what I might do is say, let's look at these 2 apparent populations, subpopulations here, this left one and this right one. And let's break them apart and look at them separately. So now I've taken a histogram of all of the times that are less than 40. And I've taken a histogram of all the times from 55 to 95, or greater than 40, basically. And when I look at this, this kind of looks like it might be an exponential. This kind of looks like it might be a normal distribution. So this kind of tells me that if I were to simulate two populations, one that is a fast exponential and a second that is a kind of slower normal, then maybe I have a better match for my system. And it can make me rethink and I think, how the heck could these two populations exist in the real world? And when I kind of think back on that, I say, you know what, maybe these people over here are the ones getting flagged for screening, for rescreening. And so they go through the metal detector, but then they have to take a trip around, get patted down, for example, and then come back through the metal detector. And I was just keeping track of when they entered the system and when they exited the system, and that lost out on all of this extra time they went through. So what I can do is I can say, well, if I can just figure out how many people go straight through the metal detector, I will give them this distribution. And if I can figure out how many people get flagged for rescreening, then I'll give them this distribution. And then I just need to create a block diagram that shows this splitting of the two populations. And so that's what I'm setting up to do here, where now I've now said, instead of having one service time, I have two service times: the long passage time, service time, the short passage time, service time, and a probability of how often they split. So I have individuals come into the metal detector, and then some get lucky enough to not get flagged, and then they get the short distribution, and some get lucky or unlucky enough to get flagged, and they get the long distribution. So that means I've got these three, this random variable, this probability. So that's, you know, technically I'm modeling a distribution here. So I have three distributions I need to worry about, not one. And so with that, I can then modify my flow chart to incorporate these. So what I'm going to do is I'm going to grab a decide block in Arena, and that decide block will be where this probability lives. And then I'm going to grab another process block. So that will be sort of maybe the short passage times. And then I might draw a second dispose block to gather the people after they exit from this new process. And what that ends up looking like is this. So this block diagram that I've put together now, I've got the same arrivals, but now they get split. And they get split by this probability right up here. And so a fraction of them go up and they take the long distribution. And the other fraction of them, the majority of them, go down and they take the short distribution. So this distribution down here, walk through, that's going to be my short distribution. It looks kind of like an exponential. And this distribution up here, get checked, that's going to be my long distribution. And so I can put two different distributions in there, let them run, and then they get collected here. And then this little number that gets collected next to the dispose block tells me how many people got checked in total and how many people walked through in total. So it's a quick spot check that I'm getting the right splits. And then likewise, that's what all the rest of these little numbers are here. So 2 have gone through this branch and 18 have gone through this branch, and they all ended up here, and these 2 all ended up here. And then 20 were created, and fortunately that's 18 plus 2. So that's what all these little numbers down here mean. So that's how I can modify this thing to better reflect this idea of splitting the populations. Now, you could say, but still, couldn't I just use the disk to begin with? What did I gain by doing this? Well, now that I have a better understanding of the mechanics of how this thing works, then I can start asking more interesting questions like, what would happen if I could change the number of people who get flagged? So maybe the reason people are getting flagged is they don't take off their shoes. Well, what if I was able to tell them more aggressively once they enter the system that they need to take off their shoes? What would be the benefit of that? And so that would affect the probability here, but it wouldn't change these two distributions. So this is a great way for me to separate my concerns out. If I just use that disk method, then if I change the probability of who gets flagged, it totally changes that whole massive monolithic distribution. But by splitting these 3 distributions out, then I can say the intervention of getting people to check their shoes more often only needs to be changed in this one spot, whereas these other two distributions can stay the same. So I can measure them separately. So it makes the modeling process easier down the line, and it makes the model a little bit more believable. And then in simulation, I can do a lot more interesting checks. So I can say, well, all right, I want to study that hypothetical scenario of what is the effect of me changing the probability of detection. Well, I can rerun my simulation as I did here with different probabilities of detection. So all three of these plots that you see here are the total passage time distribution through the metal detector, but using a single short passage time and a single large passage time, but I'm changing the probability of basically how much those two get mixed. So here I find that I've got maybe some very seasoned guests to the metal detector. So they very few detections. Maybe, so here, maybe this is like at the employee entrance of a government building. All of them know how to get through the metal detector. Over here, this might be at the public entrance to a government building. And so there, you've got some employees coming through, but a lot of people don't quite know what and they take a longer time, and maybe they need to get checked. And then over here, maybe you have, a certain time at certain times a day where you get a populate where maybe there's very few employees coming in because it's lunch break, but maybe there's a lot of other people coming in. Maybe they're from a geriatric population, a little bit of an older population that's less familiar with the technology. And so I get 90% detections during this time period. So you can see that just by changing one parameter, I get a whole slew of really interesting bimodal distributions of passage times coming out of that. Okay. So before I go on to the more advanced case, are there questions about that? Are there thoughts about what went on here? About what I meant by splitting things up and what things are being plotted here? Just to be clear, what I'm plotting here is effectively, if I take all of my entities, I can, in ARENA, you can see that at an entity level, you can see how long they took to get through the whole system. And so this is a single type of entity. So I can ask, how long did that entity take to get through the system? Now, these systems depart, or these entities depart in a different spot than these entities down here, but they're all the same type of entities. So I can ask ARENA to give me the distribution of total time in the system for all of the entities, and that's what I'm plotting down here. So any questions about that? Is it clear how we've walked through, we've turned a bimodal distribution into a couple of unimodal distributions that we have a better chance of modeling? Okay. All right, so all right, so here is a question then. What if I look at the total time in the system for the real system, and I see not just a bimodal distribution, but a multimodal distribution? So I see a bunch of peaks like this. So this is the empirical CDF over here of this histogram right here. And so if I look at this, what might be going on here? So what I'm going to do is, just to wake everybody up, is I'm going to put you into breakout rooms for about 30 seconds, just for you to chat about hypothetical reasons for why you might get this in the real system, and how we might adjust our model to accommodate for this. So I'm going to put this in the chat while we're all here, because the breakout room discussion is what causes this multimodal total time in system for the metal detector system. And this is in the real world system data. And so I will also bounce around the breakout room. It's just going to be a short breakout room, as I don't want to take too much time. But again, I want to make sure that we add a little bit more interactivity. So here we go. Okay, that'll do.
Hello, Professor. Are we in the same room? Um, all right.
Okay, so we're back. So I'd like to, I heard several different types of ideas for this. Some were ones I was expecting and some that I actually weren't expecting. So I'd love to hear some of your guys' thoughts. And so does anybody have something they're willing to offer up, either via the microphone or in the chat, however you'd like?
Our group thought of the different levels of like clearance, like TSA, pre-check, and like clear. Those ones go a lot quicker than when you're in the normal line.
Interesting. Okay, so I'm just summarizing in the chat there. So the idea here is that we've got discrete peaks because there might be discrete types of checking, and so it sounds like we're saying here that pre-check might be takes very little time, but maybe the normal time to get through is this other time here. But then we sort of have this kind of infinite sequence of these, this kind of harmonic series here. So then the question, I think that is an excellent is an excellent property that we would need to model if it was like an airport that had these different levels of service. And so that could be something that might show something similar to this. But do we have some other ideas here too? Because you might not have like like in the case of airports, you usually only have like 3 service levels. And here we've got like a lot more than them. So I also saw a comment here in the chat, like we also said there is usually a random check for some people that need to get checked extra. And so that random check is a lot like the flagging. So sometimes people get flagged because they actually trigger the metal detector, and other times they get flagged because they're just flagged for extra checking even if they don't trigger the metal detector. But still, that to me that seems like that would generate maybe 2 or 3 peaks, but not like a large sequence of peaks here. I so yeah, there's another comment here about if someone's checked, they're found to have a weapon, more time because of that situation. Again, that might generate one of these peaks. And so I definitely think that that's something you need to think about when modeling this, because those people are going to need special handling in your model. But what might generate this kind of larger sequence of peaks? And I see a couple of other things here. Time varies due to following instructions. If they don't, they could be flagged, causing more time. That's true. When I was popping around to the breakout rooms, I heard some people also talk about context differences, like different times of day and weather situations. And I thought that was an interesting answer as well. And that if these data were taken over a 24-hour period, then what we might actually be seeing here is that different staffing levels throughout the day. There could be 6 different staffing levels throughout the day, and maybe those different staffing levels correspond to different passage times. And so what we're seeing here is that there's some parts of the day when things are faster, some that are slower, and so on. I kind of would expect that if that were the case, it probably wouldn't be as discrete, like it would be kind of more smeared out. The weather thing is interesting too, like weather creates delays, but why would weather create a discrete amount of delay? That also, or if it did, I would think it would create like a very, very long delay, and that would be spread out. These kind of like short clumps of delays, I think are, kind of stretch the imagination a bit. I see some other options here. Number of items an individual has. So yeah, so I didn't mean to make it sound like this was an airport example. This was actually meant to be kind of like a government building entry example. But the idea that different people might have different things, that different amounts that they need to take out of their pockets would make them last longer. That I think is very interesting. But then you have to still say, is that going to create these discrete humps? Now there was an answer earlier that mentioned is that, that I guess I'll try to bring everybody else there too, is that if you get flagged for screening, you're often asked to go back into the line and get rescreened, and then you might get flagged again. So this particular data, so basically if I zoom in on any one of these humps, so that's what I'm going to kind of do here, is if I zoom in on this left hump, it looks like the exponential for those that just go straight through. But if I zoom in on any of the other humps, then they all kind of look very similar. It's true that one of the upper humps, so this is the 175 mean hump, it is sparser because there's just fewer data points out there, but the standard deviation is actually very similar to this hump here. And when we zoom in on each one of these individual humps, then what we find is that the individual humps are roughly the same width. So they're the same size hump, and they're each about 60 seconds apart from each other. So they're each are separated by about a minute. So if we're thinking about that, we say, well, this looks like we've got a single process that is shaped like this. So a single process that has a standard deviation of about 5 seconds in its duration here. So, so it's got whatever its average time is, it's 2.5 seconds up or 2.5 seconds back, kind of captures that. And that process seems to then get repeated for some individuals a minute after it already happened for them before. And so the thought is that maybe what we're seeing here is this cycling. So we've got someone that walks through the metal detector. If they pass, they go directly into the building. But if they get flagged, instead of being kicked out of the building, they go through a checking process and then get sent right back through the metal detector. And so the thought here is that maybe we can model the walking through the process here as the short exponential, and then the get checked process, maybe that's the thing that looks a little bit more like a bell curve that takes a little bit longer. And maybe that bell curve is sort of on average takes a minute. And so it takes a minute plus or minus some. So you walk through in about 3 seconds. And then if you get flagged, you're going to get delayed for on average a minute before you have to walk through again. And then that might happen over and over and over again. And if you have a model like this, where you're constantly cycling, and then you were to measure the total time, then you can end up getting something that looks like this. And that's actually how I generated these data, is by generating a model where individuals can get trapped in this loop, but they eventually come out, and we prioritize them so that they go through the metal detector first if they've been flagged for rescreening. And so that's what you're seeing, is that every individual goes through once, a fraction of them go through a second time, a fraction third, a fraction of that fourth, and so on. And every time they go through the metal detector, they go through a separate checking loop, which takes on average about 60 seconds plus or minus. So I hope you can, so I'll go to a question slide here. Are there questions about that? What I'm trying to motivate here is part of the reason we histogram data is that the shape of the histograms sometimes informs us as to how to build the block diagram itself. And so what we want to do is figure out a way to build the block diagram so that if possible, we can break all these processes up so that each one of them is a unimodal distribution that we have a chance at finding some known distribution to fit. Because that's going to end up being a much more reliable and generalizable model. And so when I see these multimodal, it tells me, how do I build a system that could generate these multimodal? You guys came up with a bunch of other great options too, nice of hypothetical options that we could have alternatively implemented some of your ideas in this block diagram and run them through and see what sort of distributions. And I guarantee that some of the choices you guys made would have actually also given us multimodal total time in the system. It may not have had this kind of infinite, kind of harmonic series of these little humps that keep getting smaller and smaller and smaller, but it still could generate 4 or 5 different humps. And it might be that your model is better than my model for certain systems, because my model really is specifically for this recycling situation. So are there questions about that, about how I use the more than 2 mode multimodal to inspire the idea that maybe I need this recycling? That makes sense. All right. Okay, so let's do another attendance question in the middle here, just to make sure give everybody credit who is paying attention to me throughout the whole thing. So I put the attendance question URL in here, and just to mix things up, I'm not going to ask you a question about the stuff we just did, but what I'm going to ask you here is give an example of a input model we would need to use in an inventory or supply chain system. So I mentioned, if you just think back to Lab 7, then we can think that, well, what are some examples of random variables that are necessary in almost every inventory management system? And so just give me one of those. So one of the things that you would need to find an input model for. So I'm not looking for like exponential. What I'm looking for is like inter-arrival time or something like that. So give me an example of something for an inventory management problem that you would need to find a probabilistic model for. And so I'll give you a second to do that. And then I notice I got a private question. Would there be any difference if I model the metal detector as with having a new process instead of going back and recycling? And I mean, sure, there could definitely be a difference. It's kind of like in the case of the metal detector here, I am making the claim that I can capture all of the details of this checking process by using the exact same get checked distribution. But we might find that that's actually a poor model for reality, that in reality, the second time people get checked, then they actually see a different time. Because it might be that the first time through you have to they say, okay, take off your shoes, take off your belt, etc. But then the second time you get flagged and have to go through, they'll see that you've already taken off your shoes and belt, and you have to use the wand on you. And so that wand process might be a totally different distribution here. And so we might have to keep track of how many times individuals go through. So you might need an assign block in here that increments a counter that keeps track of how many times people have been checked. And you might need another decide block that, based on the number of times people have been checked, sends them to one process or another process. So that is definitely a more realistic model. But then the question is, we want to limit how many details we put in our simulation models, if possible, if we can manage to capture the phenomena as kind of coarsely as we can. So if we need all that extra detail, sure, you could definitely put it in there and it can make a difference. But in many systems, this is going to be sufficient because hardly anyone gets checked a third time or a fourth time. So, okay, great. So I got a response back in the private chat that answered the question, so good. All right, so let's move on to the even newer content here. If I can find it, I scrolled ahead. All right, so there it here. So, okay, so as we're seeing, one of the first things you do when we go into this, you take your data and use a histogram. Just look at the shape of the data. The shape of the data are so important, whether it's symmetric, whether it's multimodal, whether it's bimodal. All of these things give you so much useful insight that you can combine with your physical intuition in building these things. And so we are going to be focusing just on this section here today. So histogram, so for continuous data, you have to be careful on your histograms because you have to choose these bin widths. And so I'll show that here in a second, the dangers of choosing different bin widths. For those of you who move on to more advanced data science, or just move on in your careers where you're going to have to be doing more of these summaries of continuous data, you might find that the tools that you provide when you generate a histogram also give you other options like kernel density estimation. And so there are ways to generate smooth histograms using these so-called kernel density estimators that are just basically ways to smooth out the bins that that we teach you about now. And so in the real world, there are ways to make this even nicer looking than a standard histogram. I'm not going to cover those in this class, but I want you to know that they're at least out there, that the histogram isn't the be all and end all of summarizing continuous data. For discrete data, you typically want to choose your bins to be the outcomes of your discrete outcomes. So you rarely want to pool outcomes together in your histogram. You want to keep those outcomes separate because each outcome kind of has its own identity. Where in the continuous one, there's no way to separate out the outcomes because there's intervals of outcomes. And so for the continuous one, you have to decide on these bins. So you're going to choose these intervals to best represent your distribution shape. This is particularly important for continuous data. And so the number of observations, that if you have more and more observations, you're going to be able to create more and more bins, more class intervals. The variance of your data. So if all of your data is clustered in one area, you're probably going to want to put a lot of bins around that area. You're probably not going to want to put that entire area into one bin. So a suggestion is for continuous data is that you create equally spaced bins that are with the number of bins being the square root of the sample size. This doesn't always work. This is just a starting point. If you have 100 points, choose 10 points and equally space them across the range of the observed data. For discrete data, typically you want to bin each outcome separately. And so as examples of that, so here's continuous data here. These are the exact same data, but we've chosen different size bins. So here I would argue the bins are probably too small because I don't kind of get an idea of what the shape is. You get a lot of noise. So if you notice, the frequency of most of these bins is 1. That means I'm just seeing a single data point. So it's almost like just plotting outliers without plotting any of the central tendencies. Here I've chosen 2 big bins. So these bins are so large that I kind of lose the shape. If I made these bins even larger, this would just look like a uniform distribution. So right now it's actually kind of, it becomes more and more difficult to tell the difference between the data and a uniform distribution the larger your bins get, because you keep sucking up more outcomes into a single bin. And so they lose their identity. And as they lose their identity, then the kind of maximum entropy assumption is that they're just distributed uniformly. So that's why things kind of look more uniform as you get more bins. So there is a sweet spot like this one here, where you choose just enough bins, just the right width of bins, that you kind of get an idea of the shape of this distribution. But knowing what this sweet spot is and where it is going to be difficult. There's no exact science. You start somewhere, and if it looks too chunky, like this one up here, you say, all right, actually add a few bins. If it looks too noisy like that, then you say, all right, let's cluster some of these bins together. Let's double our bin size, and so have the number of bins. So you kind of know it when you see it, but you want to look for something that looks kind of like this. All right, so for discrete data, we generally bin by the outcomes. And so here's a distribution. So I'll give you karmic bonus points. So they aren't real bonus points if in the chat you give me a guess for what you think this distribution is. So you can just put that in the chat, what you think this distribution is. Notice these are count data. They count from 0 arrivals per period to 11 arrivals per period. And so we've got a frequency here where it peaks around 2 or 3 arrivals per period. And so in this case, because I have known discrete outcomes, then it's best for me to bin them by outcome. I don't want to group together outcomes 0, 1, and 2 together into one big bin. I need to put a separate 0 bin, a separate 1 bin, and so on, even though the 11th bin only has 1 outcome in it. It's still important to know that I have very low probability on that outcome, but I have some probability on that outcome. So if it's discrete, bin by outcome, unless it's really, really bad. If it's continuous, then try to adjust your bin width. All right, so any guesses on this distribution? Seeing a lot of guesses for Poisson, and I like those guesses. This is a Poisson distribution. So it is the number of counts independently a number of independent arrivals you'll get in a time period as a Poisson distribution. And it generally looks kind of like this, where it usually starts at an intermediate level, it goes to a mode, and then it tails off. All right, so so once you've looked at your histogram, you do what we just talked about, what you just did in the chat. You try to kind of come up with a guess for the family here, and then you have to assess your guess, and that's what we'll do in the rest of the unit. And so inside Arena, you can go into the expression builder, which is under the tools, and they have a bunch of distributions. And if you click on them, you end up it gives you the parameters for that distribution, and you can fill in those expressions there. So we, in this unit, will be figuring out how to choose the right parameters here. And it looks like I'm not going to get through a lot of these things in detail here today. Only got 5 minutes left here. But I think we've already kind of talked about some of this here. So once you've looked at the distribution, you sort of look at the candidates for what they need to put in here. And you sort of say, well, based on these candidates, well, I'm going to use my physical intuition to try to guess, like, oh, what could it be? Well, for one, is it a discrete or a continuous? Well, that's really important to know ahead of time. So you figure that out. Do these look like they're discrete or continuous? Once they're continuous, then you can say, is it bounded? If it's bounded, then maybe a normal distribution isn't a good one, because normal distributions aren't bounded. Does it appear to be memorylessness? Or does the system appear to have memorylessness? Does the system appear to have an additive nature, like when you're assembling something? Each time you assemble something, you put one part, another part, you put them together, the handling times add up together. If it's additive, then that suggests maybe it is a normal distribution. Is it correlated with another process in the system? So you look for the context and physical properties. You use your insights about the system, and you combine that with the shape of the histogram to hopefully make a good choice. You are necessarily going to leave some details out. Your goal isn't to find the most detailed approximation of the system, it's to find the most useful approximation of the system. This goes back to saying, is it okay to just say that we recycle when I know that somebody who's passed through the metal detector a 4th time is probably going to get a totally different screening process? Well, if that happens very, very rarely, then maybe we don't need to model that. If it happens very frequently, maybe we do. So we have to decide based on how often these weird things happen if we really need to bundle them into our model. So these frequent distributions we've talked about, these are the ones you're hopefully gathering sort of familiarity with over time. All right, so discrete or continuous, I mentioned that's the most important thing. So you'll get more details of this in Lab 8, but basically the short heuristic I'll give you now is that if you histogram it and it's got a lot of data, like 1,000 samples and you're 10,000 samples, even though you've got a lot of data, there are giant gaps in between what appear to be single outcomes, then it's probably discrete. If you have a lot of data and it smoothly sweeps through a huge number of outcomes, it's probably continuous. So that's kind of your key thing. You can also plot an empirical CDF. And if your empirical CDF of a lot of data has steps, then it's probably discrete. If your empirical CDF is got a smooth rise, it's probably continuous. So that's one of the first things. And then once you know discrete or continuous, then you can go through our list of common discrete and continuous random variables and pick from there. And so again, I'm going to have to pick up, I think, with some of the rest of the stuff after in the next lecture. But what I'm going to close with is just a reminder of some of these things and a reminder that Arena has these already implemented in them. So in a normal distribution, if it's additive, for example, if it's symmetric, if someone's given you a mean and a variance, but no other information, use a normal distribution. And in Arena, there's a syntax for that, where it just takes the mean and standard deviation. An exponential, if it's memoryless, if someone's told you it's a non-negative number and they've given you an average but no other information, if it's a constant failure rate, those are terms used. These are all good things for an exponential. In the Arena, there's a syntax for that, expo. For a Weibull distribution, if you've got a failure distribution where things fail early or fail late, so you need to take a failure distribution like an exponential and reshape it, then you've got the Weibull distribution, which has got scale, which is like which is similar to an average number of failures, and shape, which is stretching those failures to happen more often or later, and so on and so forth. And so so there's a question, what indicators we use if it was Weibull instead of normal? So a key difference between Weibull and normal is that Weibull is non-negative. And so there is no risk of a Weibull distribution giving you a negative failure time. So that might be a reason why you might want to use the Weibull. A normal distribution is if you often don't know a lot about the underlying processes, but you know that they're additive, then if they've got a very large average and a very low standard deviation, you don't worry about the normal distribution bleeding into negative numbers. And so you might then use that normal distribution. So it's kind of like a Weibull distribution is one where it's customized for failure times. So if it is a failure time, it's probably better to parameterize a Weibull than a normal. But if it's some other thing, like the time it takes for me to assemble a part, then that thing might be better fit to a normal distribution because we have more physical intuition that the reason it's bell-shaped is because it's additive. So, that kind of gives you, some hints as to why one might be better than another. All right, well, we're out of time, so I will cover the plotting stuff that we will work on next time, and I'll give you the closing attendance question is just to make it quick for you guys because I'm sure you've got other places to be. Then tell me just give me an example distribution that is non-negative. So an example distribution that you're guaranteed to not generate any negative numbers if you were to choose it. And there are a bunch of different answers for that. And that's all I've got. So I can hang around for a couple of minutes if there's other questions. If not, you can feel free to pop off, and I'll see you Thursday. Remember to form your groups. Group names are due by Friday. Although they'll probably have a little bit of a grace period over the weekend, and I'll probably bug people if I don't see they've submitted that assignment. There's a spreadsheet online and some other resources for finding group members if you haven't already. All right, any other questions? Quick question on team formation. Do our group members have to be in the same assigned lab time? Oh, I apologize. That text is carried over from previous semester. I removed it from other things, but I forgot that was still an assignment. That you don't have to be in the same lab time this semester. Don't worry about that. I'll make an announcement about that too. Any other questions? All right, looks like population is decreasing rapidly, so I'm going to end the meeting and see everybody later.